So good afternoon, everyone. So I guess most of you know me either through last year's RAMTP lectures or possibly through RMOTP. So it's nice to meet you all. And this course total will have 6 lectures. I'll be giving introduction to group theory, which is part of abstract or modern algebra. So I guess you are also learning side by side linear algebra, and together hand in hand we have a nice algebra exposure. Yeah, so though it's abstract algebra, uh, I'll be doing a lot of examples and make it little easy for you. So we won't be doing too rigorous. So some part we'll do rigorously, and some part I'll stick to examples, and through examples we'll do the properties. If you have any doubts, you can raise your hand and you can ask the doubt, whatever. Yeah, so just to begin with, two nice references for group theory, or in particular for modern algebra or abstract algebra, where they talk about groups, rings, fields, modules, etc. So, one classic book is by Ian Hustin, Topics in Algebra. Another nice book is Contemporary Abstract Algebra. By Gallian. Yeah, so to start with, to begin with, these are nice books. And what we'll be doing or covering in this course, 6 lectures is following. So definition and various examples of groups. Then power of element. And order of element. Then subgroup, like every such algebraic structure always has a substructure. For groups, we have subgroups. For vector space, we have subspace, and so on. So we'll be doing subgroup, and in subgroup again, we'll be doing cosets, Lagrange's theorem. In fact, it's through the work of Lagrange and Galois and Abel, Niels Abel, foundations of group theory were laid, and later on it was made more abstract by Cayley and Dyke. Yeah, so then we'll learn concept of cyclic group. At the end, if time permits, we'll be doing isomorphism, homomorphism. Of groups. And lastly, some applications of group theory to prove certain results in number theory. So like Fermat's little theorem, or in general Euler's theorem, Wilson's theorem, etc. So some of the results in number theory will prove as application of groups. In fact, groups has applications to various fields like physics, chemistry. So wherever we come across the symmetries, rotations, etc. So their group has applications, and there are a lot of applications in physics. But of course, for Rubik cube, etc. also. But I'm not master of physics or games like Rubik cube, etc. So I will not talk about those applications. So I'll talk about applications to number theory. Yeah. So shall we start? Shall we go ahead? So this is the abstract definition of group, and something like this we have seen right from our school days. Like for example, set of integers, set of real numbers, set of rational numbers, along with operations like addition and multiplication. They satisfy similar properties. So we may not have called groups that time, but right from our school days, we have seen these properties. As I said, the roots of definition of group, or for the first time, the word group was used by Galois. And later on, in the works of Abel, we find the roots of group or group theory. So essentially, Galois as well as Abel, they were proving that for polynomials, roots by radicals, or roots in terms of the coefficients and functions. Like for example, for a quadratic, we have minus b plus minus root of b square minus 4ac by 2a. They give us the roots, and such formula is available for degree 3, degree 4 polynomials. But degree 5 onwards, there is no general formula, and this fact was to be proved. So for that purpose, in fact, what a theory developed by Abel and Galois that essentially laid the foundation of groups. And later on, it was made abstract by various people. So Cayley, around 1850, 52, Dyke, around 80, 82, gave the abstract definition of groups, or these are called as group actions. So what are axioms? Some basic statements in mathematics which we don't prove or whose truth value we accept without any proof. So assuming that they are true, based on that, whatever results we develop, they will be true. So for example, Euclid gives 5 postulates or 5 axioms for a geometry, and just like that, here we have three axioms for the group. Yeah. So first property, I hope you must be knowing names. This property is called as associativity. So we have some set G which is non-empty, and there is some binary operation. So for example, like addition on integers or addition on real numbers, rationals, multiplication, etc. So such operations, and this property is called as associativity. So A star B star C is equal to A star B star C. So I'll talk a little more about this property afterwards. So this sign stands for all. For all. And I might use similarly one more notation. So this stands for there exist. Yeah, so we have some set which is non-empty with equipped with some binary operation. I'll talk about all these things in detail afterwards. And that operation is associative. With respect to that operation, we have some element which is identity element. So like for example, with respect to addition, anything plus 0 is again that number itself. So a plus 0 is a, and 0 we call as identity for addition, or any number into 1 is itself. So like a into 1 is a, and 1 is called as multiplicative identity. So such element E is called as identity. And thirdly, for every element, there is some element B such that A star B is equal to E, B star A is equal to E. So look at both these things. By definition, identity commutes with every element. So this property is called as commutativity. A star B is same as B star A. Everything is not commutative in general. Like for example, say matrix multiplication is not commutative, or composition of functions is not commutative. But as we know, addition, multiplication, they are commutative operations on reals, integers, etc. But like for example, a minus b is not same as b minus a, or a divided by b is not same as b divided by a. So by definition, identity commutes with every element, and even inverse of element. So this is called as inverse of A. So inverse commutes by definition. So I'll try to explain the definition with the help of various examples. But before we start with examples, let me give notation. So we are following notations. Z stands for set of integers. In fact, German name for integers is Zeilen. Zeilen in German is numbers or integers. Q. And you see, in fact, these are not usual ZQ. So we have that extra line there. So these are the notations. So this is set of rationals. I hope everyone knows integers, rationals, reals, complex, and so on. R stands for set of real numbers, and C stands for set of complex numbers. So C is of the form, all numbers of the form x plus iy, where x and y are real numbers, and I is root of -1, or I square is -1. Now what we know is on all these sets we have operations like addition, multiplication, okay, and such a thing is called as binary operation. So for example, given two integers a and b, a plus b and a into b, they are again integers. So that's called as closure property. So we say set of integers is closed under addition and multiplication. So that's called as closure property. Or more generally, function is said to be binary operation if it is from set G cross G to G. So meaning thereby it will take any pair A comma B to some element again which is inside G A star. Okay. So for example, when I have two integers A and B, A plus B is again integer, A into B is again integer. Or same happens with rationals, reals, complex, and so on. So such operation is called as binary operation. And you see, actually the name itself suggests bi stands for two. So at a time you can operate on two elements. But with the help of associativity, the first property, we can define it or we can extend it to say 3 elements, 4 elements, or in general finitely many elements. So for example, we always talk of say 1 plus 2 plus 3 and so on. And what it means, at a time you can add only 2 elements. It's a binary operation. So what I can do is I can add first 1 plus 2, and to that I can add 3 later. So we get 6. Or one may say without changing the order, first add 2 and 3, get some answer and add 1 to that. So see that nowhere I'm changing the order, or I'm not, suppose A plus B, I'm not making it B plus A, I'm not changing the order. And in both cases, our answers are same. So that is just because of associativity. So I can define addition of 3 numbers. I can define addition of 4 numbers, 5 numbers, and more generally n numbers. So because of associativity, implies binary operation can be extended to, shall I say, n-ary operation. Like same thing you can't do with minus. So for example, you can't define something like subtraction of 3 numbers or subtraction of 4 numbers. That is meaningless, because if you take A minus B minus C, and if you take A minus B minus C, the two answers would be different. They are not same. Yeah, fine so far. Any doubt? I think these are basic things. So shall we go ahead?
Yes, sir.
Yeah. Okay, so now various examples of groups. So for example, set of integers under addition. Check that addition is associative. We have identity element, and namely for addition, it's 0. A plus 0 is A, and 0 plus A is A. And for every element, there is some number which you denote by minus A, such that A plus minus A is 0, as well as minus A plus A is 0. So note one thing, that identity is for the group, or it's a universal element for the group or the whole set, whereas inverse is for every element. So it's not that inverse will be common for all elements, and identity will depend on each element. Yes, Omkar?
So when rationals is not a group with multiplication because of 0.
Yeah. So in that case, idea is you throw away the unwanted elements like 0, and then it becomes a group.
Yes.
Okay, and now just on same lines, like rationals under addition is a group, reals under addition is a group, complex numbers under addition is a group. So these are all examples of groups. Yeah, so some more examples. So suppose, as Omkar is saying, suppose I try rationals under multiplication. So you see, multiplication is associative, and 1 works as identity. A into 1 is A for every element. So shall I say for every A belonging to Q? Okay. And as far as each element is concerned, trouble with inverse is like, suppose if I give you say 2 by 3, then 3 by 2 is inverse. So 2 by 3 into 3 by 2 is 1. But there is one element which does not have inverse, namely 0. So 0 into anything can't be 1. 0 into no element is 1. And therefore 0 has no inverse. But except 0, every element has multiplicative inverse. See that for each A by B, the A by B is not 0. So which means A is non-zero. B by A works as inverse. A by B into B by A will give me 1. So the idea is those elements which do not have inverse, simply throw away those elements, and the rest of the part makes it a group. So for example, Q star, and what do we mean by Q star? Q minus 0, so throw away 0, is a group under multiplication. Similarly, as far as R is concerned, real numbers are concerned, we have all properties except that 0 does not have inverse. So I'll throw away 0, R star, that is R minus 0, that is a group under multiplication. Same with complex numbers. C minus 0 is the group under multiplication. Then as far as Z is concerned, which elements won't have inverse, multiplicative inverse? So for example, suppose let's look at say 2, and I know 2 into what is 1? 2 into half is 1. But we know half is not an integer. So as far as 2 is concerned, in set of integers, 2 does not have multiplicative inverse, right? So in Z, which elements have multiplicative inverse? You can unmute and say the answer. So in Z, yeah, you can write
Can
it.
you please raise your hand? I will unmute you, please.
Sir, 1 and minus will have.
Yeah, good. So in Z, 1 and minus 1, they they have multiplicative inverse. So like 1 into 1 is 1, and minus 1 into minus 1 is 1, right? So just these two elements, and you throw away all others. So this forms a group. And in this case, there are only two elements, so it's a finite set. And once there is a finite set, a nice method to check whether it's a group or not. What you can do is write down all elements. So this is called as Cayley table or multiplication table. So 1 into 1, I'll write here, that is 1. 1 into minus 1, I'll write here, minus 1. Minus 1 into 1, I'll write here, minus 1. Minus 1 into minus 1, 1. And you see, we don't go outside the set. So product of elements 1 minus 1 is again from 1 minus 1 itself. So it's closed under the operation, right? Then associated, one has associated in original set Z, so that follows from Z. And you see one works as identity. In fact, one row of 1 or column of 1, it's just with same order. Like we have 1 minus 1, 1 into 1 is 1, 1 into minus 1 is minus. So from table, it's clear like 1 works as identity, and inverse of 1 is 1, inverse of minus 1 is minus 1, right? So this is a group. This table is called as Cayley table or composition table or multiplication table. Yeah, so these are some examples, standard examples. Any doubts so far? Now we'll do something rigorous. As far as axioms are concerned, Just see that we have just talked about existence. There exists an element in G which works as identity. So like A star E is A, E star A is A for every element. Okay, and same about inverse. Now we'll prove rigorously that identity and inverse of each element, they are unique. So definition claims that there exists some element. How many elements, that is not clear from definition, right? And just with these axioms itself, we'll prove that identity and inverse are unique. So proposition. And I'll prove one result, and similarly on same lines, you tell me for the other one. Identity element E is unique. And note, in the definition we have just said that there exists some element. And how many elements, that is not clear. So now we are proving that whenever some identity element exists in a set, in a group, it has to be unique. And these things will be done just using the group actions, only using group actions. Yeah, so proof. By definition, A star E is equal to A is equal to E star A for each and every element in G. Okay. And the idea is, suppose possible, there exists some element which to begin with, I don't know whether it is same or different. I'll just say there is some E dash belonging to G. You can use any notation. There is some E dash belonging to G, which also works as identity. So such that A star E dash is A and E dash.
So then you multiply E and E dash.
Yeah. So this is true for all A and this is true for all A. Okay. So in this first one, I'll put A equal to, or this is second one, put A equal to E dash in 1, because that is true for each and every element of G, right? Put A equal to E dash in 1. So what I'll get, E dash star E is equal to E dash. I'm replacing everywhere A by E dash. That is equal to E star E dash. I'll call this as 3. And similarly I'll do it for equation 2. So put A equal to E into, we just want to connect E and E dash, and essentially what we'll see or what we'll show is E and E dash happen to be same. So though I'm calling some element E dash as identity, essentially I end up showing E dash is same as E, so that identity element will be unique. Okay, that's the standard way to show uniqueness of. Yeah. So E star, sorry, E star E dash, I'm putting A equal to E here. E star E dash equal to E dash star E. And I'll call this as 4. And now from 3 and 4, do you see one way I get E dash star E is E dash. So I'll say E dash is E dash star E from 3. And from 4, E dash star E is E. So what I get is, even if I start with some element, calling it E dash as identity of G, essentially that E dash happens to be E itself, right? So there won't be some other element which will work as identity. Identity is unique. Is this idea clear? Now just on same lines, you tell me for inverse that inverse of each element is unique. Shall I go ahead? New page. Shall I go ahead? Yeah. So now I want proof from your side. So somebody tell me and I'll write here. So another proposition. Let G be a group. Let A belongs to G. So by definition, there exists some B belonging to G such that A star B is identity and B star A is also identity. So we call that element B as inverse of A. So to prove that inverse is unique. Shivam, do you want to say the proofs?
Yes, sir. So what we do is by definition A star B is equal to E, and which is equal to B star A. Then we assume that there is another inverse of A, which we name B
Yeah.
dash.
Yeah. So suppose there exists some element B dash in G such that yes.
Yes, sir. Such that A star B dash is equal to E, which is equal to B dash star A.
And now what
And then
we want to show?
so we want to show that a B dash is equal to B.
Yes. So we'll show that B dash is same as B.
Yes, sir. So, and by definition, we know that A into B is also E, and B, which is equal to B star A.
Yeah.
So
maybe
one of
I'll
these,
call this as 1 and I'll call this as 2.
yes,
So
sir.
you can say by 1 and 2 also. Yeah.
So that means that A into B dash is equal to A into B because E is the common term.
A into
B is equal to A into B dash. Sorry, A star B is equal to A star B dash. And then we cancel out the A's and B is equal to B dash.
cancellation is not defined in the actions.
Oh,
So I mean, we have to justify that cancellation.
You can multiply both sides by B or B dash.
Then what will happen?
Then the A times B and A times B on both sides will become E, and that will, then you will get B equal to B dash.
Just tell me from the beginning. So our aim is to show that B dash is same as.
Sir, we can consider equation 1, multiply both sides by B dash. Then we also know that A into B dash is identity. Therefore, we get that B is equal to B dash.
Just a minute. So what did you say? Multiply first by? Multiply first one by?
Yes, so we can multiply the first equation on both sides by b dash.
Okay, just a minute. So whether I should multiply on the right side or left side, which way?
Both sides. Okay, the earlier a into b is equal to e.
So no, here what I'm saying is whether I should multiply from this side or I should multiply from this side.
Sir,
Uh,
it's associative. So
Yes, it's associative, so
And it's associative, but
it's not commutative.
not commutative. In general, it may not be commutative.
I guess can multiply from any side.
Okay. Okay. So A star B dash is equal to E star B dash.
Oh no, then it won't. You'll have to take it from the start itself, like on the left side, multiply on the left side.
Yeah. So B dash star A star B is equal to B dash star E.
Yes, sir. Now the right side will become b dash, and left side you can take the brackets around b dash and it's a.
So why right side becomes B dash? Because that is by definition of identity, right? And on the right hand side, what we can do is this is B dash star A star B. So what I'm using associativity. So we need essentially associativity for various purposes in the group. Now B dash star A is E by 2. So I get E star B is equal to B dash. But E star B is again B by definition. So B is equal to B dash. Right? Or I mean, same thing I can say starting with B and ending with B dash. So start with B. So shall I say B is equal to B star E? And that E I can replace by A star B dash. But I can say this is same as B star A star B dash. B star A is E star B dash. And E star B dash is B dash. So essentially I get B is same as B dash. Or you can go this way, vice versa. And you can show that B dash is B. So though we start with some element B dash, which works also as inverse, essentially that B dash turns out to be same as B. So this means inverse is unique. Usually inverse of A is shown by A raised to -1. That is standard notation for inverse, or many times if operation is additive, it's shown by -A. So this is standard notation for inverse. So usually for proofs in group theory, we prefer multiplicative notation, and every time we may not write star star. So in that case, we use this notation for inverse, A inverse. And if group is additive, we use minus additive notation. This is for multiplicative notation. Yeah, shall we go ahead? So anybody has any doubt? Okay. Yes, so we'll define one more term, abelian group. It's in honor of Abel. Abel was a Norwegian mathematician. Niels Henrik Abel. He was from Norway. And very recently, in his honor, Norwegian government has started Abel Prize for mathematics. So great work in mathematics. Like there is no Nobel for mathematics, and something like Nobel they wanted to start. So idea was proposed almost 100 years back by the then king of Norway, but it materialized very recently, uh, around 2000. So first Abel Prize was given in 2003. Like in 2007, it was awarded to one Indian mathematician, statistician, V.R.S. Vardhan. For his work in probability and statistics. Yeah. So, as I said, certain problems of roots of polynomial in terms of coefficients. In fact, Abel got the idea that group should be abelian. In that case, the roots can be given in terms of the coefficients, and we wanted this condition. So later on, in fact, Jordan called such groups as abelian groups. So where we have A star B is B star A. So like for example, what are groups we have seen so far? Addition is commutative. So Z, Q, R, C under addition are all abelian. Or 1 minus 1, Q star, R star, C star under multiplication are all abelian. So we'll do some examples of non-abelian group later. But for the timing, I hope you are studying matrices also in other courses.
Yes, sir.
So if I take say 2 cross 2 matrices with non-zero determinant. Why non-zero? Because in that case inverse exists. So GL2R is all 2 cross 2 matrices ABCD. And the determinant AD minus BC should be non-zero. So this is a group under multiplication, matrix multiplication. And this is non-abelian because we know for matrices in general AB is not same as B. So this is non-abelian group.
So what have we written this GL2?
So that's notation for that group. Like we say Q for rasters, R for reals, C for complex. So on same lines, that is called as general linear group of matrices of order 2 cross 2. So more generally, GLN stands for n cross n matrices. So that is just notation for that group. Yeah. Later on, we'll see some more groups. Okay, so here is one more concept, order of group. The number of elements in a group G is called as order of G. It's denoted by mod G or O of G, order of G. If order of G is n for some natural, we say G is a finite group. So for example, order of 1 minus 1 is 2. Otherwise, it is called as infinite group. So Z, Q, R, C, Q star, R star, C star, these are all infinite groups. Order is infinite. So we write this way, order of G is infinite. And many times results for finite and infinite groups will be different. Yeah, so what things we saw so far, like definition of group, various properties like inverse, identity. Then identity is for the whole group. It's a common element for the whole group. Inverse is for each element. All right. Then we have concept of commutativity per group. That's called as abelian group. And we have proved that identity and inverse are unique elements. And here is one more concept, order of group. Fine so far? Okay. So we'll do some of these examples and add to particular cases. So I'll do Zn for n equal to 4 or maybe n equal to 5. I'll explain what is u of Zn. So later on in our course, we'll see various examples from here. I'll do special case of Dn today. So as I said, we'll do some of these examples and we'll try to understand groups with the help of examples because it is abstract concept. So let's start with Zn. And what it is, I won't explain right now. We'll do particular case and in general, I'll say what is Zn. Yeah, so I hope all of you know the congruence relation in integers. We say A is congruent to B mod some natural number if n divides A minus B. Everyone knows congruence relation. Is there anybody who doesn't know congruence? What is congruence? Yeah. So I assume that everyone knows these things. Right? And in particular, let's deal with case n equal to 4. So A is congruent to B mod 4 if 4 divides the difference A minus B. And then we know that A is always congruent to itself. That is called as reflexivity. So we say congruence is reflexive relation. If A is congruent to B mod 4, then that implies B is also congruent to A mod 4. So we say congruence is symmetric. So that's property called as symmetry property. And if A is congruent to B mod 4 and B is congruent to C mod 4, that implies A is congruent to C mod 4. So that's called as transitivity, or we say congruence is transitive. And once some relation satisfies three properties, reflexivity, symmetry, and transitivity, that is called as equivalence relation. So congruence is equivalence relation. And every equivalence relation partitions the whole set into classes, equivalence classes. So even set of integers gets partitioned into classes. So let's see what are the classes. Yeah, so I'll denote it by 0 bar or bracket 0. So this is standard notation. So 0 bar is class of 0, and which means those integers which are congruent to 0 mod 2. So that means 4 divides a minus 0, right? And what will be these elements? They'll be essentially all multiples of 4, right? So these are all 4k type elements. What is class of 1? So those integers which are congruent to 1 mod. So say for example 1, 5, 9, 13, and so on. So those elements which are 4k plus 1 type, that will form class of 1. Or essentially those which leave remainder 0, that is class of 0. Those which leave remainder 1, that is class of 1. And similarly, what will get class of 2? They are 4k plus 2 type elements. And class of 3, they are 4k plus 3 type elements. What is class of 4? Class of 4 will be again class of 0, right? So those which are 4k type elements. So essentially, modulo 4, I get 4 classes, and this set I denote by Z4 or Z mod 4. So there are standard notations as Z by 4Z or Z4. So a more convenient notation is Z4 right now. And what I mean by Z4 is the remainder classes 0 bar, 1 bar, 2 bar, 3 bar. So when I divide by 4, modulo 4, I have 4 classes, essentially 4k type numbers, 4k plus 1 type numbers, 4k plus 2 type numbers, 4k plus 3 type numbers. And more generally, Zn will be set of remainder classes modulo n. So what classes I'll get? Class of 0, class of 1, class of 2, up to class of, what will be last? Class of
N minus 1.
n minus 1. Class of n will be same as class of 0. Everyone follows this?
Yes.
And then with respect to addition modulo 4, we'll show that Z4 forms a group. And more generally, with respect to addition modulo n, one can show that Zn forms a group. So let's try to see using tables. So easiest way is to form KD table. So it's addition modulo 4. 0 bar plus 0 bar is 0 bar, 1 bar, 2 bar, 3 bar. Then I add 1 bar to every element. 1 bar plus 0 bar is 1 bar. 1 bar plus 1 bar is 2 bar. 1 bar plus 2 bar is 3 bar. And what is 1 bar plus 3 bar? That is essentially,
0 bar.
yeah. So that is 0 bar. So every element of the type 4k plus 1, when I add it to 4k plus 3 type element, what I get is 4k type element. So that is 4k plus 0. So leaving remainder 0, right? So see that it's closed under the operation. I don't go outside the set. Addition of such classes again turns out to be class within the set. Yeah, so this is 2 bar. 2 bar plus 1 bar is 3 bar. 2 bar plus 2 bar is 0 bar. Or you initially call it as 4 bar, but 4 bar is again 0 bar. 2 plus 3 is 5. 5 is like class of 1, right? Then this is class of 3. 3 plus 1 is 0. 3 plus 2 is 5. 5 is 1. 3 plus 3 is 6. 6 is 2. I hope everyone gets the table. And you see now from the very table, you can see that 0 bar works as identity. Associativity, you can check case by case because there are finitely many elements. So you simply say associativity can be checked because it's a finite set. And for each element, there is additive inverse. So like inverse of 0 bar is what is inverse of 0 bar?
0 bar.
Yeah, 0 bar. More generally, inverse of identity is identity itself because E star E will be E, obviously. Right? So inverse of identity is always identity. Inverse of 1 bar is, which you can read from the table, 1 bar plus what gives me 0 bar? 1 bar plus 3 bar gives me 0 bar. So inverse of 1 bar is 3 bar, and therefore inverse of 3 bar is 1 bar. Inverse of 2 bar is 2 plus what is 0?
2 bar.
Yeah. So inverse of 2 bar is 2 bar. So it forms a group. So Z4 under addition modulo 4 is a group. And what is order of this group? Order of Z4 is number of elements in that group. So that is 4. Is it abelian? Basically addition. So A bar plus B bar is same as B bar plus A bar. Or you can see from table, if your ith row is same as ith column. So first row is same as first column. Second row is same as second column. Third row is same as third column. If your ith row will be same as ith column, then that is basically abelian or commutative. So Z4 is abelian. Okay. Now more generally, let me say about Zn. So Zn is set of all remainder classes modulo n. So n minus 1 bar under addition modulo n is an abelian group of order n. Order n. Okay. So maybe like Z4, you can try to prove on your own in general that Zn is a group. Yeah. So now let's check for multiplication. So Z4 under multiplication modulo 4. So just on same lines, you can form a table, KD table. Zero into zero, zero, zero into anything is zero. So even column will be zero because I know multiplication of integers is commutative. 1 bar into 1 bar is 1 bar, 2 bar, 3 bar. So I know this column also is again same 1 bar, 2 bar, 3 bar. 2 bar into 2 bar,
0 bar.
0 bar. 2 bar into 3 bar, 6 bar, that is 2 bar. This is again 2 bar. 3 bar into 3 bar is 3 3s
1
are
bar.
9. Yeah, 9. 9 is 1 modulo 4. So I'm looking at remainders modulo 4, right? And do you see, like in this case, it's not a group. Essentially, every element does not have multiplicative inverse. And we have same idea, like 0 has no inverse, 2 has no inverse, right? And throw away those elements which do not have inverse, and the other elements form a group. So for example, let me throw away 0 and 2, and that will form a group. Right? Let me throw away this. And throw away 2 also, because 2 does not have inverse. And you see now whatever table left, that is surely a group. In fact, let me tell you a nice criteria for a finite set. If you form a table, if every element occurs in each row and each column exactly once, then that's a group. So now you see this is a group. 1 bar, 3 bar. So see that answers are once again inside the set. So answers are again 1 bar, 3 bar. So they are again inside the set. And 1 bar has inverse, that is 1 bar itself. 3 bar has inverse, that is 3 bar itself. So this is called as U of Z4. U stands for units or invertible elements. U of Z4, that is 1 bar, 3 bar, forms a group under multiplication. Modulo 4. Okay. And from number theory, what condition we know in general in Zn, which elements have multiplicative inverse? So A bar has inverse modulo n, modulo n. If and only, what is the condition?
If it is co-prime with n.
Yeah, so GCD of A and N is 1. Okay. In fact, what happens is once GCD is 1, what I get is by Bezo's theorem, some combination of A and N, some AX plus NY is 1. And therefore, when I work modulo N, what I get is AX is 1 mod N, or basically classes of, so it's like A bar into X bar is 1 bar in terms of classes, and therefore A bar has inverse. A bar into something is
Could you explain how 1 bar plus 3 bar is 3 bar?
1 bar. Acha, you want this table for
So is this addition or multiplication?
multiplication?
Okay.
Okay, so more generally, A bar has inverse modulo n if and only if GCD of A and n is 1. And I'll call that set as U of Zn. I'll try to go back and try.
So, and what does that U represent?
So U stands for units, or units are like invertible elements. So U of Zn is those A bars belonging to Zn for which GCD of A and n is 1. And this is a group under multiplication modulo n. Is abelian group of order. Now, how many elements have GCD 1? That is denoted by Euler's pi function. Pi of n. So number of elements is denoted by pi. That's called as Euler's pi function. Okay, so you can find, say, U of Z by U of Z6, and you can form tables and verify yourself that it forms a group. Yeah, so we'll talk about one more group. Sorry. Yeah, so we talk about symmetries of equilateral triangle. And more generally, you can talk of symmetries of square, a regular pentagon, a regular hexagon, and so on, or more generally regular n-gon. Yeah, so what do we mean by symmetries? So I have a figure in a plane. So what is equilateral triangle? All angles are equal, all sides will be equal. And let me name them as, say, number 1, vertex number 1, vertex number 2, vertex number 3. And if I rotate the whole diagram in a plane, so like for example, if I rotate around the centroid, if I rotate by some angle, I'll get something like this. And you see, when I rotate by 120 degree, again it will fit onto itself. 1 will go on to 2, 2 will go on to 3, 3 will go on to 1. So just convince yourself that when you rotate by 120 degree, it will fit onto itself. So such an operation is called as symmetry of that diagram. Or it's like from a plane you can cut the original triangle, and when you try to fit into that hole again, essentially when you rotate by 120, it fits again into that gap. That is called as symmetry. Okay, so I'll represent it this way. So rotate one rotation by 120 degree. So it's either called as rotation by 120 degree, rho 120, or sometimes it is just called as rho 1. So I'll call it as rho 1. Rho stands for rotation, and I'll denote it this way. 1, 2, 3, vertex 1 goes to 2, vertex 2 goes to 3, vertex 3 goes to 1. Then once again, if I rotate by one more 120, so together I mean total 240 degree, that will again fit onto original figure. That will be also symmetry of equilateral triangle. So one will go to 3, right? 2 will go to 1, and 3 will go to 2. Is that clear? Maybe I'll erase those arrows. Yeah. So 1, 2, 3, 1 goes to 3, 2 goes to 1, 3 goes to 2. It's rotation by 240 or a double rotation. Then if I rotate it 3 times, it's as good as no rotation. It's original diagram. So I'll call it 0, rho naught. So should I say 1 goes to 1? If I rotate it 3 times, again 1 gets placed onto its original position. 2 goes to 2 itself, 3 goes to 3. What else? Any other symmetries so that the figure fits onto itself? So we have these 3 rotations and there will be in fact 3 reflections. So for example, if I place a mirror at this place, so vertex 1 here, I place a mirror, and if I take mirror image along that mirror, so this line will fit onto this line, this part will fit onto this part, and vice versa. This line will fit onto this line, and that will be a symmetry of equilateral triangle, right? So in that case, what happens as far as vertices are concerned? So I'll say mirror at vertex 1, where 1 is unmoved, one stays onto 1 itself, but see that vertex 2 will go on to 3 and vertex 3 will go on to 2. Okay, this will fit onto this and this will fit onto this. Is that okay?
Yes, sir.
So that's called as mirror at 1. I'll call it mu1. Similarly, I can place mirror at 2. And what will be mu2? So 2 is fixed. The point which lies on the mirror is fixed, and the other 2 will get exchanged among themselves. So 1 goes to 3, 3 goes to 1. Mu3, where 3 is fixed. 1 goes to 2, 2 goes to 1. And if I compose any 2 of these symmetries, that will again give me answer from itself. So like for example, if I rotate by 120 and then take mirror image along vertex 1, original position, that will again give me one of these functions. So it's closed under the composition of these functions, and we can form a table. So if you form a table, you can see that it forms a group, and that group is called as D3. So symmetries of a 3-gon. More generally, Dn stands for symmetries of n-gon, regular n-gon. So Dn stands for symmetries of regular n-gon. And what will be order? So it's of order 2n. Why 2n? There are n rotations and there will be n reflections along either n vertices, or in case of even case, like for example, for a square, I don't have axis passing through the vertex. I have reflection along these lines, right? Yes, so symmetries of regular n-gon. I have n rotations and n reflections. So it's of order 2n. And in general, one can see that it is non-abelian. Non-abelian. So let's try to compose table here. That's a nice exercise. Yeah, shall I go to next page?
Yes, sir.
So let me show as an example. So for example, mu1 composite row 1, and it's like composition of functions. So first you perform this operation, then you perform this operation. So it's in reverse order. What is row 1? Rotation by 120 degrees. So 1 goes to 2, 2 goes to 3, 3 goes to 1. What is mu1? 1 fix, 2 goes to 3, 3 goes to 2. Okay, and you can do it this way. So first 1 will go to 2 under this, and then under this 2 will go to 3. So 1 goes to 2, 2 goes to 3. So together 1 goes to 3. Then 2 goes to 3, 3 goes to 2. 2 goes to 3, and that 3 goes to 2 here. Okay, so finally 2 goes to 2. And 3 goes to 1, and 1 goes to 1. So finally 3 goes to 1. Okay. 3 goes to 1. So you see this is again out of those symmetries. So this is basically.
So won't you do the mirror first and then the rotation, or is it the other way?
So rotation first and mirror later. So we do it like composition of functions, FOG. So first operate this function, then operate this function.
Oh, yes.
Or I mean, if you define it that way, like a mirror first and then rotation, that also will define a group. Only thing, table will be different. Yeah, so what is this? Shall I say this is mu2, 2 fix, 1 goes to 3, 3 goes to 1. So this is mu2. Okay. And let's check, say, row 1, mu1. Mu1 is 1 fix, 2 goes to 3, 3 goes to 2. So row 1 is 1, 2, 3, 2, 3, 1. Yeah, so everyone, 1 goes to 1. I'll first operate in right side and then to left side. I'll go reverse this way, right? So 1 goes to 1, and look at image of 1 here. 1 goes to 2. So finally 1 goes to 2. Okay. And you can prepare some equilateral triangle on your own with some cardboard or something, and you can try these actually working, and you'll exactly get the same positions. Yes, so 2 goes to 3, and then 3 goes to 1. So finally 2 goes to 1. 3 goes to 2, and 2 goes to 3. So finally 3 goes to 3. And you see this is mu3. So operation is not commutative. So mu1 row 1 is not same as row 1 mu1. Right? It's not abelian. It forms a group, but it's not abelian. Yes, I'll just give a start, and later on you can complete at home later the whole table and see that it's a group. And whenever you finish, you can see there is nice symmetry and nice structure for that table also. Yes, I'll write composition. So we have elements row 0, row 1, row 2, mu1, mu2, mu3, row 0, row 1, row 2, mu1, mu2, mu3. So I'll write row 1 into mu1 here, row 1 mu1 here. And what is that? Row 1 into mu1 is mu2. Sorry, mu3. Right? Row 1 mu1 is mu3. So I'll write here mu3. Right? And mu1 into row 1, I'll write here. That is mu2. Okay? This is mu2. So you can complete the table later at your leisure and see that it forms a group. In fact, every element occurs in each row, each column exactly once, and that forms a group. So see that, complete the table, that is homework, complete the table and see that it forms a group.
Could you repeat what the symbol for this group is?
Almost. So D3. So D stands for dihedral group. And it's the smallest non-abelian group. So this is non-abelian. So in fact, one can show that group of order 1, 2, 3, 4, 5 is always abelian, and the smallest non-abelian group is in fact D3. So group of order 6.
Sir, it's time.
Yes. So I'll stop.
I wanted to ask, what does the circle stand for? The function.
What?
The function for this group, that small circle.
And that is composition of. So this is called as composition of functions.
Okay. Yes, sir.
Yeah, so let's stop here. You can complete this and next time we'll continue. Maybe if I get time, I'll explain the table once again. Bye for today.
Thank you, sir.
Bye, sir.